So, my name is Sarot Srong. Sarot is my given name. So, the lecture today is Kalman filter, application in estimation and sensor fusion. So, I presume that all of you are from robotics and IT pathway. So that's great. And the objective for this lecture is to raise awareness of some practical challenges and to introduce you a method or algorithm that have been widely used in many research fields, especially in the field of robotics navigation for robot for uh, spacecraft or aircraft. Um, so before I jump to the lecture, let me briefly introduce myself. Uh, sorry, not this one. Yeah, I have been working for ITC for 8 years after I graduated my PhD. And now I'm the head of ECOM engineering program in Phnom Penh, Cambodia. And I'm also the head of a laboratory that I founded in 2000, at the end of 2015. It's called Dynamic and Control. Uh, yeah, if you want to see more about myself and my team and my laboratory, you can go to the website, DCLab ITC UK. So we have several projects, partly related to the development only. Some of them are research. Yeah, for the robot and UAV are very research intensive, but for other just development for student to join robot contest or something like that. Okay, here is the content of my lecture today. I will start with the introduction by giving you some applications in many research fields. Then I will briefly review some fundamental theory, Gaussian distribution, and conditional probability to warm up because this is what you studied maybe 2 years ago. And then I will introduce a Bayesian filter for linear system, and then the main the core of the lecture today is the Kalman filter based on the theory of Bayesian filter, and then I will give illustrative examples, and I will end this lecture by some key takeaways. Here, the introduction. So, Kalman filter is a probabilistic state estimation technique. It can be used in sensor fusion. Sensor fusion means I give an example for localization of a robot. So from the wheel of the robot, we can put the answer to measure velocity. From kinematic, can interpret into the motion, the velocity of the robot itself in the space. But at the same time, we have other sensor on board can measure acceleration, for example, IMU, and then we can integrate it to compute the velocity as well. So two type of sensor, but can be used to compute the same thing. So we can implement the algorithm to get a better estimation because all sensors are corrupted by noise. And for the state estimation, actually state and parameter can be estimated as long as we make the model properly, and also system identification. Let's say we have a device or something that we model it as a black box, and then we want to identify parameter inside, then we can use a Kalman filter. And interestingly, the first application of Kalman filter actually to solve the space navigation problem. Um, Kalman filter is named after Rudolf Kalman, who introduced this approach in 1960, and the first application is for Apollo project in 1961. So you can imagine that if you use onboard sensor to compute the location of a spacecraft, there are so much noise, so it's not easy to localize the aircraft, the spacecraft in the space frame. Uh, so Kalman filter introduced to filter out the noise. So let's say if this is true or trajectory, but what we have measured is very random around the true trajectory. But Kalman filter is used to estimate the trajectory that close to the true one, something like that. And here are some applications that Kalman filter have been widely used. You can see like altitude heading reference, I mean the direction, the heading of a spacecraft or aircraft with respect to the north axis, um, dynamic positioning, even in macroeconomics, time series econometrics, orbit determination of satellite or rocket, radar tracker, satellite navigation, simultaneous localization and mapping, SLAM. This is specifically for vehicle. Yeah, can be mobile robot or can be unmanned aerial vehicle. And it has been interestingly, it has been used for U.S. Navy nuclear ballistic missile submarine. Well, I just want to raise awareness that this algorithm is very powerful. Has been used in many applications. It doesn't mean I'm fancy of a missile or something. Yeah, and for attitude control, it means control the orientation and navigation of spacecraft for docking with International Space Station. And I only use Wikipedia as a source of reference because it's easy for you to search for this if you are interested to know more. Okay, then the next part, which is a brief fundamental of Gaussian and normal distribution. Um, I'll give you one example to illustrate this fundamental. Let's say if we have a voltage generator, we want to generate as a sine wave, and the load is just as resistant. So using Ohm's law, the current pass through the resistance is supposed to be sine wave as well, right? But when we put the sensor to measure the current, it never pure sine wave. It's always corrupted by noise. So what you have measured must look like this. So it means a combination of the pure sine wave, the deterministic one, and the corrupted noise, like this. And so if we look in detail into the statistical information of the noise, if you plot the histogram of the noise, you can see that the data that around zero appear the highest frequency. Okay, the more data around the value zero appear at highest rate, and other, for example, data here may be almost zero, right? That's why the frequency is zero, like this. Okay, so this region represent the value of this noise from this to this. So this is the scale of this noise itself in this axis. So interestingly, that most of noise take the form of bell shape, and it can be modeled by Gaussian distribution. Okay, so this is the Gaussian distribution probability density. So this one is density. Okay, probability density. Um, and for each, yeah, you notice the mean value of this probability density is this value zero here. Yeah, it's here. Also zero here. But for h, the mean value of h is this deterministic actually. This h bar is deterministic one, and this h is what we measure and corrupted by noise, which is this one. Okay, so this represent the probability density function of uh, this data. And here is the review of some operation on random variables. Well, the first one is expectation. Um, by this formulation, if you know the probability density of one random variable, then you take the integral in the entire space by that density times that h. This is like gravity, right? If you think that uh, think this is density of gravity, yeah, a material that has the highest concentration or the highest density, so the gravity would be, the center of gravity would be close to that zone, something like that. Yeah, same thing. And variance means how much the 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 uh, the randomness of the data away from the mean value, how large it is. If variance is large, it means our data very noisy. If variance is small, it means it's close, very close to the mean value, something like that. So I can illustrate by this graph. For example, the mean value is at this straight line, and if our data around here is not so far from this line, it means variance is small. But this one is a little bit larger, so variance of this one should be larger than variance of this one. Okay. Um, and if we look at the density in one dimension, yeah, I saw earlier. Yes, this is one dimension. Um, oh well. So the operation of expectation can be computed for mean if we put the inside integral like this. And if we want to compute covariance or variance, if I say variant, if the variable is only h, we say variant. If we have h and y, then we say covariance. So we use the same operation, expectation, but it just the function inside is different. Okay, so you can see that the noisy data minus the mean value, it means like, and we put the square, it's like distance square. Okay, this distance plus this distance plus this distance, something like that. Okay, if in multi dimensions, it take the form of vector, and this is the norm of the two vector, the difference of two vectors. Okay. um, and if we look at the undimensioned, uh, to illustrate easily, to visualize it, to be able to visualize it, we can only use only two dimension. We cannot imagine in, because two dimension for the state, for the random variable h1 and h2, and the third dimension is the density itself. So if you look at here, you can see that the highest density is here. It means this h1 and h2 are noisy data, but it appear around here the most often, most frequent. It appear around here. Okay, and so if the covariant matrix take the diagonal value like this, only diagonal, it means that the shadow of an ellipse here is aligned, that the principal axis of the ellipse here aligned with the axis of h1 and h2. Okay, but if the covariant matrix has off diagonal value, the ellipse, it rotates like this, the shade like this. So it means data of h1 and h2 appear most frequent around this zone, around this ellipse, and the highest appearance of the data is around here. It's like that. And so to warm up a little bit of the concept of conditional probability, I will give you this example. Uh, let's say we conduct experiment of this system that this, I call this sphere, white sphere, this gray sphere, this gray box, and this white box. Okay. Let's say when we put all these items on the table. When the light is on, we can see how many gray square, how many white square, and white box something. So we can easily compute the probability of, as you can see here, box, gray, and white. Probability of gray box must be 4 divided by the total age. Okay, and so we can have the prior knowledge. But then if I turn the lights off, it's dark, so you cannot see the color, right? Then you conduct experiment just to catch it, and you feel that, oh, this is square. And then if somebody asks you what is the probability that this square is gray, then we can easily compute using the prior knowledge. So this table gives you the prior knowledge, right? Um, Prior knowledge, so probability of gray box is 4 over 8, probability of white sphere is 2 over 8, something like that. And now we use a conditional. We conduct experiment, we take it once, and then we know that it's square, and then we want to compute what is the probability of this square is gray. Then if we look at the table, we can easily compute that uh, because this is sphere, all the sphere only 3, right? And the gray sphere from the prior knowledge only 1. So probability is 1 over 3. Okay. So this is very intuitive from this table. But when we want to use a formulation using the prior knowledge that probability of joint event, gray box, gray sphere, okay, is 1 over 8. And the prior knowledge of probability of uh, sphere, okay, B a sphere is something, okay. So we can just divide it, then we get the conditional probability. So I mean, you can imagine that given some knowledge, when we conduct experiment, we get some information. From given this information, what is the probability of other event, something like that. Okay. So yeah, if we look at here, gray sphere join together, gray and sphere is 1 over 8, and probability of sphere, all sphere is 3 over 8. So 3 over 8 here, and then it's also 1 over 3. Okay, so I hope you got the idea of conditional probability. Because later on you can see many things, too many mathematics in Kalman filter. But yeah, I write it very detailed, but you don't need to care about the detail, but because I will try to explain the concept, so you just try to catch up the concept, and you can look at the detail later. Now let's look at dynamic system. So for linear system, we can model it as discrete, and what usually if we don't consider noise, consider uncertainty, the model is called deterministic. That is very simplified model. Okay? But if we want to simulate the system to be to uh, account for uncertainty, for noise, then we call the system is stochastic. We add the noise term like this. This is for state equation, and this is for output equation, or output equation means something that we can measure. So for linear system, what we can measure, it can be part of the state that describe all the motion, all the dynamic behavior. So let's take a motion for a mobile robot. To describe the whole motion, we need only 3 variables. Uh, I think 6. Okay, 6. Position, x, y, and orientation, and then the velocity along the x, velocity along y, and velocity and angular velocity of rotation in the 2D. But if we want to describe the motion of a unmanned aerial vehicle in space, we need 12 state variable to describe the motion. Okay. So H here represents the state, represent all the variable that needed to describe the dynamic, and Y is output. Yeah, it's something that we can measure. Okay. So um, in real life, it's always difficult. It's not easy. So we usually try to simplify that, introduce a deterministic model, and we can compute it. We can compute this recursively. K represent the time instant. So from k minus 1 to k, in between that, there is a sample time, let's say 10 millisecond. At this instant, we compute h. At the next 10 millisecond, we compute another h using the previous known h, something like that. Okay. And for the deterministics, you have to simplify to see the behavior. But in reality, let's say, just consider one DC motor. When we put input voltage, it rotates, and we have sensor in, like, technically called encoder to measure the angle. And yeah, so you imagine, the model of the motor, you put the voltage, you measure position, and what you have mathematical modeling for it, and you have a system for experiment. Do you think the angle that you measure and what you compute always the same? Of course not, right? And the more time pass, the higher the gap, right? The higher the gap. This is what it means. The true one is stochastic, but we, in order to simplify, to study the behavior, we use just deterministic model. But here, to test Kalman filter algorithm, we need to simulate the stochastic system. We add some random data that we don't know. Okay. And we represent it as a true one, because the true one we never know, right? We never know. And then we have model and put random number in there, so it becomes something that we never know, right? Yeah. um and another one is continuous. This one is discrete, this one is continuous. So from physics, electrical circuit, DC motor, or dynamic model for mobile robot, or for UAV, for aircraft, always in continuous differential equation. Okay. But we have a way, engineer always has a way to solve a difficult problem, that if we want to compute it, we just use Euler approximation. Okay. We call Euler approximation if the model is deterministic, and if the model is stochastic, we call Euler Maruyama. Okay. Almost same, but there is a difference on the noise term. That's why it has a name Maruyama in here. So here I illustrate the difference between model, because model is a nice mathematical model. So let's say we compute a dynamic model that has input as a sine wave. The blue one represents, like, the model that we compute using the mathematical model. Okay. And if we add noise to the dynamic equations and we compute with the randomness of the noise, then we got the trajectory of it is something like the orange color here. Okay. So the true and deterministic not the same. And for this system, it does not drift away from each other, but some system will drift away each other. Yeah. And okay, here just an uncertainty on the dynamic model itself. But then if we want to measure something, our sensor also introduce some corrupted data, some noise. So the orange here is the true state is, and then we want to measure it, and then we got additional noise here. Okay, the orange one, very noisy. So the blue deterministic output in here, but I made a wrong display. I displayed the orange after, so it cover all the blue here. Yeah, but you can now if you notice, you can see the blue here. The blue here is just like the blue there because I measure it directly. I make assumption that I measure the H directly. Um, this is the main idea that that come up that the filter is introduced. So H should be estimated. This H should be estimated. And what we know is the model that we compute to get the blue, right? We want to estimate the orange, but what we can compute from the deterministic model is the blue. And what we can measure is the orange here. Okay. So information that we can have the blue in here, and we can have the orange noisy here. But then we want to estimate the orange here. Okay. So H, the true state of the true state that describe the dynamic behavior should be estimated, and Y is observed. Y can be measured. So here there is a probability density given H. If H is given, then we can compute probability that Y can occur. Okay, because we have the model relationship H and Y. Okay, so the estimation rule must be a function of Y, because Y we can uh, compute the predicted output, and also we have measure the Y, but they must be different. So from that information, the information of Y, we will estimate H. It's like from the information of the experiment that it is a sphere, and then we compute the probability for that sphere is gray. So let's say gray like H, something like that. Okay, and yeah, it's even H, and Y is experiment that we can know only sphere or box because it's dark, right? When we get it, it's dark, we can only touch it, something like that. And the idea is the criterion is to minimize covariance, or variance is is a scalar. To minimize the variance, it means uh, I can show here again. Here, to have the best estimate, so I draw another line here. Do you think this line and this line, which one has better smaller covariance or variance? Because variance is the sum of distance square, right? Distance square like this. Okay, distance square to the line. But if I have a line here, the estimate of h hat here, you can see the line here is very far away, right? Far away. So this one is not the best estimate because it's not the variance is not the minimum value. But for this line, it has the minimum value of variance. So here is the idea. Oops. Yeah, the idea here is to minimize the variance, and the solution is very nice, very not intuitive, but when we know it, yeah, it should be like that. Actually, the solution is just expectation of H given the measurement Y. See? Yeah, given this measurement, if we have model, we can predict Y. But when we do the experiment, we got the value Y. Then we just use operation expectation of H given Y. Then we get the best estimate. Yes. Yeah, there is a proof. It's a little bit mathematics, but I can explain the idea. Uh, well, first, let's see estimation, expectation of a function of H and Y. H is state that describe the dynamic behavior. Y is the model, the output model. Okay, that because Y we can measure, Y we can also compute from the state. Um, so operation expectation is because we have two random variable H and Y. Then the expectation operation is integral entire space for the density of joint density of H and Y. times this function. Yeah, this function. Okay. And then we use the conditional probability, the formulation is probability of x given y equal to joint probability h and y divided by probability y. Or we can say probability of joint h and y equal to probability of h given y times probability density of y. Okay. And we split like this, and here, because y is known, y is given, then this function is just function of h, and we take the integral entire space of h. So this is just expectation, one expectation of h yeah, of f h y. But let's say y is given, but y can happen in the entire space, and then we look at the outside integral, the integral entire space for y. It is another expectation. So finally, I cannot erase here. Yeah. So finally, it's just expectation twice for this function given the event y. Yeah, but the inside expectation is we y is given, and the outside expectation is operate on the y itself. And then we do the expectation. We check the expectation of a function gy that g of y, that is estimation rule with respect to the noisy h. Okay, noisy variable h. We just do some trick, minus this and plus this again, it will be the same, and then expand it, because the norm square can be rewritten as one vector transpose, yeah, to be row vector, and time the vector which is column, also row this side, column this side, from the side, and then it means the norm square. From like that, finally, uh, yeah, this part is 0, because this one is just number, because we already make one expectation is a number, and expectation of this h is given y, it's the same thing as this one, that's why this is 0. And now we only have this expectation of these two term, um, but this term is independent of y. Okay, this term is the no, so let's see here. Yeah, there is another, yeah, just split expectation inside here, this one with for this, and this one for this here, and then this term is irrelevant to g of y. Yeah, irrelevant to this one. So finally, to have minimum value of this one, this must equal to this. Okay, and this means expectation of h given y. Yeah, so this is the idea for the filtering. It's conditional expectation. Um, so here I try to illustrate how do you read this kind of expectation of h given y. Let's say we have joint density h and y. It means h and y appear very often in the ellipse shape here, but it more often here, right? More often it is appear here. But if when we conduct experiment, we got y is this value. Let's say y is 3 given y, then the density is marginally uh, becoming the green one, like this, still bear shape. So given y this value, what is the value of h that give the highest probability? So h here, right? H here give the highest probability. So this is the meaning of expectation of h given y. Once we find the joint probability density, we can compute. Yeah, so here is the main idea. Um, for the filtering, okay, for filtering, Bayesian filter. So in our dynamic system, we know we give the input, and then the system behave that is described by state variable h. Okay, um, and y can be measured. Y could be part of the state or could be combination of the state that describe the behavior of the dynamic. So the filter separate into part. One is time update. Time update means um, we have the model hk in terms of hk minus 1. Okay, and it has a uncertainty term. Then if we want to find the expectation of this h given, yeah, with the knowledge of h at time k minus 1, we compute the expectation of h in the next time step. Okay, given the input, so g is the collection of input and output from 1 up to the time k. So if gk minus 1, it means collection of input and measurement up from time 1 up to time k minus 1. So then we apply the operation of expectation, which introduce the density here. So this one is called prior knowledge. Uh, because we compute recursively. So if when we start from 1, we give the priori, we can just give any number that actually is not true. But because the algorithm is very powerful, the priori or the posteriori or converge the probability. The covariance converge, but probability is higher and higher, something like that. So this is called priori. Uh, you priori that obtained from the previous time step. Yeah, it means like that. Um, so actually, yeah, so you can forget this, can forget these two lines, but just say, okay, expectation of at the time k given measurement up to time k minus 1. If you have the model AH plus BU, it's still AH plus BU. You can say, just say that. For because the noise term here, the noise terms here, if Gaussian, expectation of Gaussian, the mean is 0. The noise is always around 0 like this. Yeah. So Bayesian filter is for general, but if the noise is Gaussian, we can simplify something. Computation become easier like that. Um, then what we compute expectation of it, we must have the information that this estimation is has big error or small error. So we need to bring along the information of the error that is represented by covariant matrix P. So we use the operation expectation on this formulation that I showed earlier. And yeah, because the model, it has the stochastic model has a noise term, the estimation got from the ball here, and we subtract this, cancel out, and then take a as a factor, and then this one store the information of covariance of the priori covariance. Yeah, this one should be k minus 1 given measurement up to time k minus 1. So yeah, the check here and the check here will be the part of the algorithm. And next, for the measurement update. Yeah, measurement update. First, we compute the expectation of output. If we have the expectation of it like this, and we know the model of the output, then we can compute the predicted output, right? So actually, it's just simple like this. The model is c times x. So then the expectation of y here is just c times the expectation of h, because this one is 0 as well if Gaussian. And then we compute, because now we propagate h to y, so we got the information, the error information h and y together, right? So it called cross covariant between h and y, and then the variance between y and y itself, because y can be the combination of many h. So among themselves, so h uh, propagate the error to the predicted y. So we got the covariant information, the error for the cross covariant between h and y, and then variant between output y themselves, and also the measure, the variance, the covariant of the noise when we conduct experiment. Okay. Um, Again, if the distribution is not Gaussian, the method to compute even much more difficult. So that's why Kalman filter choose the most simple one for the filtering problem. So if, yeah, so one we have the information h y h hat, yeah, here it should be h hat, y hat, and we have the covariant and cross covariant. Then we can construct joint probability of h and y. Okay, construct joint probability in y, illustrated by this curve again. Then upon the receipt of the new measurement yk, it means y is given, yk is given here, yk is given. Then we find what is the best estimate h such that the probability density is the highest. Okay, so upon the new measurement yk, we compute h hat, and we compute the update covariant of the green one. Okay, so the information that we need to propagate recursively are means and covariance. So yeah, using some calculation, some calculus, but it's a very huge derivation. Then here is the update state. So state here is compute based on the state model, but of course it, as you can see before, this is deterministic. You based on model, deterministic model, and this is true. So if we don't correct it, maybe I just pick a point based on model. Okay, from this point to this point based on model, but based on the uh, measurement y, measure, this is hk given k minus 1, and when we compute predicted y compared with measurement y is not the same, which means the true h is not here, the true h is somewhere else. So that we need to correct this one, by the measurement term here. This is measurement, new measurement, this is predicted measurement, predicted output, and they are not the same. So we correct it by Kalman gain, this one called Kalman gain. And Kalman gain is just product of cross covariant and inverse of variant of output. And also we correct the probability, the priori covariance. Okay, this one is the priori, and this one become the posteriori. Okay, we correct this one as well. So here the summary of process of filtering. So from the prior knowledge of the state, they join as a probability density function like this. So this is we view from the top, from the axis of density. Then we can see the shape as a ellipse like this. So this priori covariance and mean. So this mean means we estimate this h, and at the same time we provide the information that this kid could be wrong at this amount. So p store the information of how much our estimation is wrong, something like that. And based on physical model, we can compute propagated covariance through the model and propagated mean. And then upon the new measurement yk, we update this prediction, okay, by this formulation just so earlier, the same formulation. And then the output of our system is this term, the output estimate of state. This is just additional information of Kalman gain here. And here the summary. So actually, if you are good at simulation, good at programming, maybe you can forget all the thing before. But if you know the process, how to compute here, that's all. You can apply it. So there's three main steps, but the initial estimation we compute only once. Then we jump to the time step. Time step we can compute based on the model. You don't need to care the subscription here, because it's recursive. I mean, the h new replace the old h, so you can just use h like that. Why like that? It's okay for the programming, but here it's just to explain you in detail what it means, what all they mean. So that's why I draw here as a loop. It means you compute here for at time k minus 1, and then you go back, go back to time update and repeat all. So k is just move from 1 up to whatever number you like. So between k, let's say k 1 2 3 4 5. So between 2 to 3, in the dynamic system, actually you have a sample time like 10 milliseconds, for example. In some system you need even smaller sample time, but some system, for example, weather forecast. For weather forecast, the sample time can be in hours. Okay, but for control motion, for motor or something, sample time should be 10 millisecond or smaller, or maybe 40 millisecond is fine for some not so high speed robot. Yeah. So this is a note. Minimum variance estimation is given by a conditional mean, that the main idea. And yeah, how can we calculate conditional mean? Well, even we know the probability density function. For example, if it's a uh, Poisson distribution or Gaussian distribution, even though we know the calculation is difficult, actually in general it's very difficult. Only the PDF is Gaussian, then the calculation is easy. Easy means we can use calculus, normal analytical calculus, to rewrite all the equations. But if the distribution is not Gaussian, for example, Cauchy distribution, we can never use analytical method to rewrite it. We can only use numerical method to compute everything. So here is one example of differential equation. Here is the dynamic equation for the state, just first order, and this is input. Let's say we give the input 10 sine t. So then the solution of h here somehow in the sine wave as well. Yeah, at the steady state is supposed to be sine wave. And let's say we can measure h directly. Okay. So now we know a is -1, b is 10, sine t is u, we can use that. And c is just 1 because we measure h directly. And then we do the discretization for computation. Okay. Just make discretization using Euler approximation to have this discrete model. Then we can implement Kalman filter directly. I don't have the car. Okay, so this is just deterministic model. I mean, when we compute it, we got a nice sine wave, a pure sine wave, like that. But then if we model it as a stochastic, we add noise term. And for the output equation also have noise term. And this one, in if we use MATLAB, we just use random n like this. Okay, random with n here means normal distribution. Without n, the random would be uniform random, so it's not right. So from here to here is the process of discretization using Euler Maruyama. And yeah, the deterministic part, it is the same as Euler approximation, but for the noise term, when we discretize, then the sample times just appear here with this q. So there is a long uh, theory about this kind of noise. It's called Brownian motion. Actually, this one is called Brownian motion. So it's long lecture about Brownian motion. But for practical person like me, I just know how to compute and then use it. Yeah, again, from that model, we compute the deterministic blue one, and this the orange one represent the true state, and the orange here represent we want to measure h directly, but the sensor tell us with some noise data. And then when I apply Kalman filter, because Kalman filter try to estimate the true state. So here the blue is the true computed from the stochastic model, and the orange one is obtained from Kalman filter. So it's very close, like this. Okay. And the estimated output here, see, you can see, estimate output become the filters data from the noisy measurement. So in many feedback control system, if we use very noisy measurement for the feedback, perhaps we cannot get a high performance because we cannot increase the controller gain, because this controller gain is too high, especially when we have derivative controller. I think you already learned the control theory one, already know derivative. It's very sensitive to noise, because if we look closely one point to another point with the noise, you can see the slope is very high. So it means the derivative term is very high. So that feedback control using the direct measurement is not always good. Most of the time it's bad. Then filter the filter algorithm is needed most of the time. For nonlinear system, so far I only show linear system because it's much easier uh, to look into the linear system than nonlinear. But anyhow, we can extend it from what we have for linear system to nonlinear system. Actually, the problem is that in the nonlinear system, we just do not know A and C. But when we estimate H for another time step using the nonlinear model, that's fine. But we don't know how to propagate the error information. I mean, propagation of covariant matrix of this time step to the prediction in the next time step. So we just do the linearization, use the Jacobian linearization of nonlinear function. So the Jacobian become a square matrix A here like this, and we evaluate it at the last known estimate. Okay, evaluate at the last known estimate, and then we just use this A for the normal Kalman filter algorithm. That's it, and we call it extended Kalman filter. Uh, this example is to show you that not only we can not only can we measure or can we estimate state, at the same time we can estimate parameter. For example, here I have parameter A, I have parameter B. So for simulated true system, okay, we know A, we know B, we put there, we compute there, we know what for reference to compare. Okay, and we for the output we use the data that corrupted by noise, and then we implement Kalman filter that we don't use the same A, the same B, we just estimate any A, any B at the beginning, just says all zero. Okay, and we just know the model, we remodel, we choose A as a state, B also as a state 2 3, and rewrite the differential equation like this. Because A is constant, so h2 dot mean A dot is 0, h3 dot is 0. So A here is h2 appear here, h3 appear here like this. So it become third order differential equation. Okay, then we have the model like this one, the standard model discrete, but just we have 3 states, and but because of this term it become nonlinear. Just because of this term become nonlinear, and then we need to use linearization to find the matrix A, and then we can implement Kalman filter, and then we can estimate state and parameter at the same time. Like here first, yeah. So here is the true state, the true parameter orange and red here, red orange here, straight because they are constant. And in a Kalman filter algorithm, we initially we estimate that it's all zero, but then it jump like this, and then it convert to the true parameter, and the state we can also estimate at the same time. So this is very useful when we have a divided. We know the model, but we don't know all the parameter, so we can somehow make lump sum the lump parameter for the model, then we can estimate the state and the parameter at the same time. So we just know the input that we need to give it, and we can measure the output. Okay. So here is one application in sensor fusion. This robot has wheel encoder that can measure the angle and velocity of the wheel, and then we can compute the velocity of the robot, and at the same time we use the onboard IMU. So IMU has gyroscope. Yeah, IMU has gyroscope. Gyroscope can measure the angle. So we want to know the heading with respect to the absolute frame to the north, actually. Because it has a magnetic sensor, it can measure the angle with respect to the north axis. But it has noise, of course. So we want to use the information from encoder and from the IMU. So and we only choose for the heading actually. So why we need the fusion? Why wheel encoder is not enough? Wheel encoder is incremental. It means even a slice error, but when it rotate longer and longer, the error accumulate over time, right? Accumulate over time. So yeah, like this one. This is the simulation that if we use only one encoder, and we put some noise to encoder, and then the trajectory is like this. I mean, the information from encoder tell us that the position of robot is like that. Yeah. Um. Okay. So here is the application in sensor fusion one. Yeah, this one. What I want to. Oh, for the gyroscope. And so why not just use gyroscope? IMU. Um, when the robot is at rest, encoder can tell us the exact zero of velocity, but IMU does not. It says a small number of velocity or angle because it has a little noise. It means it's telling us that the robot is having motion a little bit, but it's not true, right? So at the low velocity or yeah, at the low velocity or at rest, encoder information is good, but IMU information is not good. But when robot move fast, the wheel may have slippery, so the information from encoder is wrong, much wrong. But the IMU can give better information. So we choose these two to have a better estimate of the localization. So this one is also sensor fusion using three sensors: IMU, encoder, and LiDAR sensor. But we only conducted the simulation. So from robot kinematics and dynamic inside a framework that yeah, a framework that already exists. The dynamic no sorry the dynamic model exists inside the environment already. Then we can compute the velocity, and then we interpret all the velocity as a encoder data. We interpret into a LiDAR signal, we interpret into a IMU signal, and then we add noise. After we add noise, then we use Kalman filter to filter out noise and fuse multiple sensor because all sensor has their own noise like that. Then we fuse together. And so here this illustration, when we add noise for one sensor like the encoder only, then the localization of the yeah localization given by encoder only is like this. But when we fuse multiple sensor, then we can have a localization better like this. Okay, here this one is the last slide, the key takeaway. Uh, okay, the first one, Kalman filter has been applied in wide range of application. You can see in at the beginning, and the fundamental filter is recursive Bayesian filter, but with assumption of Gaussian noise for both process. Process means the state equation, and measurement noise, measurement in the output equation. Then the Bayesian filter become Kalman filter. And the calculation of mean and covariance is easy in this case. Um, the classical Kalman filter is used for linear discrete system only. However, for continuous system model, we can do the discretization before implementing the classical Kalman filter. By linearizing at the last known estimate, Jacobian matrix can be computed and use for computing covariance update. So if the state equation is nonlinear, we can do the linearization to find the Jacobian matrix. And even if we have the output equation as a nonlinear function, we can also do the same thing, okay, to get the matrix C, so that we can update covariant matrix. And the algorithm is called extended Kalman filter. And there are many practical challenges in the localization of vehicle that require multiple sensors, and sensor fusion algorithm such as Kalman filter is needed. Yeah, and uh, in the modern navigation system, for a mobile robot or for self-driving car, they use encoder and camera, so all that can interpret into uh, via the kinematic, via image processing, and then kinematics. Then we can compute the velocity of the vehicle, and from the wheel encoder or tachometer, we can also compute the velocity of vehicle, and then we can fuse to have a better estimate of localization. And for cube satellite, small satellite, because small satellite, we need to use small IMU, inertial measurement unit, and this small sensor has a lot of noise. That's why we need so the hardware is worse. Then we need a better algorithm. It's like that. For big satellite, a big aircraft, we use a very good IMU, so we don't need sophisticated algorithm. But when we shrink down the size, then we need to use smaller sensor, and the performance of sensor is not so good. Then we need better algorithm to deal with it. Okay, so that's all for my lecture today. Thank you for your participation. Yeah, we still have time for question and answer. Yeah.